In this lesson, we are going to learn about nuclear fission. Fission means breaking up. Fission is initiated when a heavy nucleus like uranium-235 captures a slow neutron, that is also known as thermal neutron, because the energy is in the thermal range. When this uranium-235 captures a slow neutron, it becomes uranium-236. Write the mass number in kgs by 1. This nucleus is unstable. It breaks into some x plus y, plus you get 2.5 neutrons on an average. This takes place in 10 to the power minus 12 seconds. Very, very fast. If you remember, electron jumps from a higher energy level to a lower energy level in 10 to the power minus 8 seconds. When a nucleus emits an alpha particle or a beta particle, it goes to an excited state and jumps back in 10 to the power minus 10 seconds. But here, this intermediate nucleus breaks up into two parts and it produces neutrons, 2.5 neutrons on an average in 10 to the power minus 12 seconds. This X and Y can be 90 different kinds of nuclei. X and Y are not fixed. And some reactions will get 2 neutrons. Other reactions will get 3 neutrons. So the average is 2.5 neutrons. Now, these are called fission fragments. These fission fragments fly out with lot of energy, kinetic energy. Neutrons also pick some energy. And these fission fragments are typically radioactive. So some energy goes as radioactivity of fission fragments. So from where is this energy coming? This energy is coming because the total mass of daughter nuclei, including these neutrons, is less than the mass of parent nucleus. And the difference in mass, that is called mass defect, that is released as energy. The energy is the energy equivalent to mass defect. Okay, mass defect is mass of all these things minus the mass of this nucleus. The binding energy per nucleon of daughter nuclei is more than 0.9 MeV compared to parent nucleus, and this results in the release of energy. This is called nuclear fission. One example of nuclear fission, we can take some example of X and Y. If you look at uranium-236, this can break up into barium and krypton, plus you get 3 neutrons in that particular reaction. This will be 36, 92. This will be, look at, total is how much? 92. So 92 will give us 6 here, 56, right? And what will be the mass number? 95 we got here. So subtract 95 from here. You get 141. So this is an example of a reaction. There can be so many different kinds of reactions. 90 different kinds of daughter nuclei we can have. So this is nuclear fission. nuclear fission is initiated when a heavy nucleus like uranium-235 captures a slow neutron. This is called thermal neutron. Then it breaks up into two parts, which are not at the extreme, they are in the middle of the periodic table, you can say. Like they are broken up into barium and krypton. And we get an average of 2.5 neutrons in this nuclear fission reaction. And we get an energy which is 200 million electron volts, 200 mega electron volt, huge amount of energy per reaction. That is coming because the combined mass of daughter nuclei is less than the mass of parent nucleus, and that mass is converted to energy. Now, because neutrons are produced in this reaction and a neutron is required to start the reaction, we can have a chain reaction. You understand that? One neutron will start this reaction, and from the reaction you will get an average of 2.5 neutrons, sometimes 2 neutrons, sometimes 3 neutrons. So that can cause 2 to 3 more reactions. This way we can have chain reaction. Suppose the sample size is small. These neutrons can escape without causing further fission. Then the reaction will not continue further. But if sample size is big, then many neutrons will not escape. So we can have a chain reaction. We need a size about the size of a cricket ball for chain reaction to start. That size is called critical size. Suppose you have got a U-235 sample of the size of a cricket ball, then chain reaction will start and you have an atom bomb. Boom! Right? In an atom bomb, 2 pieces of U-235 are brought together rapidly to form a mass more than critical size, that is approximately the size of a cricket ball. And that's how we get an atom bomb. Now, in a nuclear reactor, we don't want such a situation to arise. We want the reaction to be steady and controlled. 1 neutron per fission should produce the next fission. The remaining should either escape or should be absorbed. So how do you do this? We have got neutron absorbing rods of boron steel. So some neutrons will get absorbed by these neutron absorbing rods. Next, we want the neutrons to slow down, because fast neutrons can fission U-238 also. Now you don't want fission of U-238, you want only U-235 to fission. So for slowing down neutrons, we use something called moderator. Graphite core is used as a moderator to slow down neutrons. Heavy water, D2O, that is also used for this purpose. Moderator slows down neutrons so that you have fission of only U-235 and don't have fission of U-238. Remember, in nature, 99.3% is U-238. Only 0.7% is U-235. U-235 fissions with slow neutrons. In fact, plutonium-239 also fissions with slow neutrons. U-238 fissions with fast neutrons. For an atom bomb, you need U-235, and separation of these two is not easy because chemically you cannot separate them. They got the same chemical properties. So you have to use some physical techniques to separate these two. That is where the real technology is. Initially, when this technology was developed, it should take very long time to separate these two isotopes. The first atom bomb that was dropped at Hiroshima was based on uranium-235. For the second atom bomb, they did not have sufficient enriched uranium, and that was based on plutonium-239. Plutonium-239 also fissions with slow neutrons. So therefore, in a nuclear reactor, we have got neutron absorbing rods of boron steel. We have got moderators to slow down neutrons, graphite core and heavy water. We also have got cadmium rods. Cadmium rods absorb neutrons and they are used for control. So if the reaction is getting more violent, you dip the cadmium rods inside. The reaction is less violent, you take out the cadmium rods. The first nuclear reactor was built at the University of Chicago in 1942. So in this lesson, we have learnt about nuclear fission. Fission is initiated when a heavy nucleus captures a slow neutron, that is thermal neutron. The heavy nucleus breaks into two parts. Those are called daughter nuclei. And these daughter nuclei fly away at very high speeds. Most of the energy released is released as kinetic energy of fission fragments. Some energy goes as kinetic energy of neutrons, and some energy goes as radioactivity of fission fragments. The energy comes from mass defect. Mass defect is mass of these daughter nuclei minus the mass of parent nucleus. The binding energy per nucleon of daughter nuclei is more by 0.9 MeV per nucleon compared to binding energy of parent nucleus. We get 200 MeV of energy per reaction. Then we learnt about chain reaction. A neutron is required to start the reaction and more number of neutrons are produced in the reaction. Therefore, we can have a chain reaction. If the sample size is small, most of the neutrons will escape. If the sample size is big, bigger than critical size, the size of a cricket ball, we will have a chain reaction, and that is what is an atom bomb. Right? In a nuclear reactor, we want a steady and controlled reaction. For that, we have got neutron absorbing rods of boron steel. We also have got moderators to slow down neutrons, graphite core and heavy water are used for this purpose. We have got control rods of cadmium which absorb neutrons again to control the reaction. So this is nuclear fission. In this lesson, we are going to learn about nuclear fusion. Nuclear fusion means two light nuclei are combining to form a heavy nucleus. Right? Remember that graph of EB by A, binding energy per nucleon against mass number, which is the number of nucleons. So this is the graph. As we go from here to here, binding energy per nucleon is increasing, and that is what is nuclear fusion. Okay, when you go from here to here, it is fission, this is fusion. So nuclear fusion is when two or more light nuclei combine to form a heavy nucleus. This is the source of energy in sun, stars, hydrogen bomb. One example of nuclear fusion reaction is two deuterium atoms or two deuterium nuclei rather combining to form a helium nucleus plus we get one neutron. Binding energy per nucleon of this is more than this. Mass of this is less than mass of this. Please understand that carefully. Mass of this plus this is less than mass of this plus this. The difference in mass is converted to energy. binding energy per nucleon of this is more than binding energy per nucleon of these two. And that's why we get energy in this particular reaction. In this reaction we get 3.3 MeV of energy. You may think that is less. In fission we got 200 MeV of energy per reaction. Here you are getting 3.3 MeV of energy per reaction. That may disappoint you, right? But actually, look at the mass of these two. Compare that with the mass of uranium-235 that underwent fission. The energy released per unit mass in fusion is more than the energy released per unit mass in fission. So in this process, per unit mass, you get more energy. Now these two will not combine easily, right? Because there is an electrostatic force of repulsion between them. To make them combine, we need a very high temperature, 10 to the power 8 to 10 to the power 9 Kelvin. Right? You cannot imagine this temperature. Now how will you get this temperature? On Earth we get this temperature by nuclear fission. You start a nuclear fission reaction, get this temperature, then fusion will start. In the sun the temperature is little bit less. The temperature of the core of the sun may be around 10 to the power 7 Kelvin. There the reaction is taking place at a slightly lower temperature because of huge number of deuterium atoms. Right? So many nuclei are there, so they can collide and the reaction takes place. So this is nuclear fusion. This is the source of energy in hydrogen bomb, in sun, in stars. Everywhere nuclear fusion reaction is taking place. Now, people have not been able to build a nuclear fusion reactor, a controlled nuclear fusion reactor so far. If that is built, it will be a very good source of clean energy, because here the products are not dangerous, they are not radioactive that way. If you build a controlled nuclear fusion reactor, definitely you will get a Nobel Prize. Right? That is be such an important discovery. We have got controlled nuclear fission reactors. But the problem with them is that the products that we get are radioactive and they are dangerous. People talk about nuclear waste. And that's the main problem with these nuclear reactors. They are dangerous kind of things. This will be giving you products which are not dangerous. So try and build a controlled nuclear fusion reactor one day and get a Nobel Prize.